In this video, we will present our progress on the design and validation of an omnidirectional magnetic induction antenna. In current applications of underwater communications, autonomous underwater vehicles, AUVs, communicate with each other in deep water to collect and deliver big ocean data. In our proposed scenario, coil-based magnetic induction is used for communication between AUVs. In order to maximize induction, the coils must be positioned in parallel with each other, as there are no induced signals between orthogonal coils. Even though AUVs can adjust themselves to improve reception, this will dramatically challenge the control of AUVs underwater. A possible solution is to make the transmitting and receiving antennas omnidirectional, that is, they can receive a signal from any direction. In practical applications, the antenna is usually integrated on the surface of AUVs. However, the metallic AUV's surface strongly reflects incident signals, which will make the received signal very small and even suffer from environmental noise. To solve this problem, ferrite materials with high relative permeability are used to assist the coils to improve reception. We have done much work on antenna design, especially in simulation. The following is the outline for our presentation. First, we will introduce our proposed tridirectional antenna prototype. Then, a comparison of signal reception performance between the coils with and without ferrite is given to demonstrate the enhancing effect of ferrite. Afterwards, the signal propagation between AUVs is investigated in air and in the ocean. Finally, we will provide some real-time experiments to validate our simulation results. In our scenario, the transmitter and receiver antennas consist of 3 coils with a radius of 5 centimeters, which are oriented into 3 orthogonal axes. As shown in the figure, the transmitter and receiver are 3/10 of a meter apart and are operating at 100 kHz. When the transmitter coils are rotated in the 3 axes, a signal that covers all directions in the domain will be produced. Then, we measure the induced voltage on the 3 receiving coils to examine if a good signal was obtained. In our simulation, we first use 1 coil as the receiver. As shown in the next figure, the induced voltage is plotted when TX1, TX2, and TX3 are rotated. Since TX1 is always orthogonal to RXY, the red curve is almost 0. For the other 2 curves, they have obvious zeros at specific rotation angles. In the second case, we use 3 coils as receiver. There are still zeros when we add the induced voltages on 3 coils. However, we can guarantee for at any rotation angle, at least 1 coil can receive the incident signal well. In the bottom right figure, the induced voltage is almost constant when we add the absolute values together. This comparison shows that the 3 coils enhances reception performance. In this section, we integrated the tridimensional antenna on an AUV. In our simulation, we used a metallic body to mimic the AUV surface. Furthermore, ferrite materials with high relative permeability are used to improve reception performance. In order to test the omnidirectivity of the receiving antenna, we put the transmitter, which is the same as the previous one, in 2 different locations relative to the AUV. In the first case, the transmitter is placed in the Y direction and is half a meter apart from the receiver. In the second case, the transmitter is in the Z direction and they are also half a meter apart. The 3 transmitter coils are rotated just as the previous section. Then, the induced voltages on the receivers are measured. In case 1, we use only 1 coil and then use 3 coils. The results are similar to the previous section. 1 coil receiver has strong directivity, but the 3 coil receiver can receive the incident signal very well. Similarly, in the second case, even though the transmitter is placed at a different location, the receiver has almost the same reception performance. This means the transmitter location does not affect receiver performance. After that, we compared the induced voltage on the receiver with the addition of ferrite. 2 pairs of coils are used to obtain the induced voltage. First, TX2 and RXY are used as transmitter and receiver, respectively. Then, TX3 and RXY are used as the transmitter and receiver. From the figures on the right, we can conclude that ferrite cores can enhance the received signal compared to the coil without ferrite cores. Afterwards, we investigated the signal propagation between AUVs. We changed the distance between AUVs and measured the induced voltage on the receiving coils. We used two conformal antennas as shown in the figure. In the air, the two antennas are placed parallel at first and then perpendicular. The amplitude of the received signal decreases when the distance increases. The figure on the bottom right shows that the three coils are omnidirectional, but one coil is not. Similarly, the same conclusion can be made when the antennas are placed in the ocean. We compared the two cases in the previous two slides and found that the signal decayed faster in the ocean than in the air. That is reasonable since the ocean water is a lossy medium. In our simulation, we used tridirectional antennas as the transmitter and receiver. They both contain three coils positioned in three directions. Here is our tridirectional antenna. It is used as a receiver, and the location is fixed. The single coil is used as transmitter. The input signal is a 3 volt 100 kHz sinusoidal signal and is marked by the yellow curve. At first, the transmitter is parallel with this coil, thus the green curve is non-zero. However, the other two are orthogonal to the transmitter, hence they receive almost no signal. Similarly, when we rotate the transmitter, the same responses are shown in the screen. That is, only one coil received a non-zero signal. The transmitter is rotated like the simulations. As you can see from the oscilloscope, no matter what the rotation angle is, at least one coil on the receiver can induce voltage. To solve the signal reflection caused by metallic surfaces, ferrite materials with high relative permeability are used to assist coil reception. We used a PVC pipe covered with aluminum foil to mimic a real AUV. Only one coil is deployed on the pipe surface. We use one coil as transmitter and the pipe coil as receiver. They are placed in the same plane to maximize coupling. First, 3 ferrite cores are placed between the aluminum foil and the coil, that is, the black thin sheets. The induced voltage is about 167 millivolts. Then, we gradually remove all ferrite cores. The induced voltage is reduced by half after one ferrite core is removed. After the third one is removed, the signal suffers from noise and cannot be recognized. The induced voltage on the receiving coil is 30 millivolts without ferrite. In this experiment, we can conclude that our proposed tridirectional antenna can overcome the problem of antenna directivity. Also, ferrite materials can assist antenna reception. After that, we designed an underwater testbed. A single coil was fixed in a remotely operated vehicle, ROV, and used as a transmitter. For convenience, the receiving node was placed near the surface of the water. The ROV establishes communication with the node and transmits a BPSK signal. We explored the signal intensity with the change of distance between transmitter and receiver. As shown in the figure, we found that signal intensity decreases as the distance increases. It is reasonable and consistent with the simulation results. In the future, we will improve our testbed, especially with the underwater experiments. We will involve more powerful control algorithms to achieve AUV localization and path planning algorithms such that the AUV can travel between several sensor nodes and collect data.